Space Symposium in Colorado this week, 30,000 satellites. That's where the Space Force says we're heading. But the problem is, tracking that environment is about to get a lot more complex. So how can we actually keep up? Hi, I'm Dr. Amanda Analytics, and I break down what's really happening in AI, space, and data, so you can understand the systems behind the headlines. Let's start with what we can actually see today. According to Orbiting Now, we're tracking around 16,000 objects in orbit, and that includes active satellites, inactive satellites, and debris. So this is what's publicly visible using standard tracking data. But it's important to understand this is only part of the picture. Systems like SpaceTrack, which is maintained by the 18th Space Defense Squadron of the United States Space Force, and SAIC maintain a much larger catalog of objects, including smaller debris and fragments that aren't always reflected in simplified visualizations. So when we talk about tracking, yes, we're talking about satellites, but we're also thinking about the entire orbital environment. Now layer on what came out of Space Symposium. According to the United States Space Force, reported through Breaking Defense, projections show over 30,000 satellites are projected to be in orbit by 2040, along with a major expansion in missions like communications, missile defense, and orbital operations. So we're moving from a world where we're publicly tracking around 16,000 objects to one where we'll have over 30,000 satellites alone. And that doesn't even include debris. This means in addition to tracking more satellites, the challenge for us is managing a much larger, much more complex orbital environment. And this is why we're starting to see new tracking capabilities emerge. One example is Lookup, which announced this week during the Space Symposium in a press release that their SORASYS 1 radar is now operational, and it's designed to detect and track objects in low Earth orbit, including small debris. This is a ground-based radar system, which means it can operate continuously day or night and isn't dependent on lighting conditions the way optical systems are. They're targeting down to around 10 centimeters, which is right at the threshold where debris becomes mission critical from a collision standpoint, because objects at that size can still cause catastrophic damage in orbit. Now, while detecting smaller objects is a major step forward, we need to ensure that we have reliable tracking and we're able to make decisions at scale. Lookup is expanding into the United States market, which is significant because this is one of the most advanced and operationally demanding space situational environments in the world. So the real test is how well the data that we're intercepting integrates into existing systems and supports real-time operational decision-making. This is where the next challenge comes in and where my research happens to be focused. So in my PhD work on space situational awareness, I looked at how to better organize and categorize orbital debris using machine learning, specifically clustering techniques like DB scan and anomaly detection. And I did this in order to improve conjunction assessments and risk prioritization. And so as we detect and track more objects, the focus shifts to optimizing how we use the data at scale. And so as we're able to track smaller objects, we also increase visibility, but we also have a significant increase in data complexity. So in my research, I showed that grouping debris into clusters, such as stable objects, anomalies, specialized patterns of behavior, and high risk, as we look at the debris, we can make conjunction assessments more targeted and efficient. So more data does not automatically lead to better decisions. We have to make sure we make appropriate sense of that data. So with tens of thousands of satellites and millions of debris objects projected, the environment becomes increasingly complex, requiring faster and more precise decision-making to operate safely. This level of growth is fundamentally changing how space operates. And so with this being said, I'm interested in your perspective. How quickly can tracking systems adapt to this level of growth in orbit? Would love to hear your thoughts in the comments. Please share below. And if you would like to see more breakdowns happening on what we're actually seeing in space, AI, and data, make sure to like, subscribe, and follow along. Would love to hear your thoughts in the comments. Thanks for tuning in. Take care.